Good morning, everybody. My name is CH Vinay Bharadwaj, and I am from Triple E first year of Section A. Today, I am going to explain about Physics PPT, and my topic is about semiconductor quantum dots. Generally, what is meant by semiconductor quantum dots? Semiconductor quantum dots are nanoscale material clusters compound of 10 square to 10 to the power of 5 atoms. The size of the quantum dots is orders of magnitude larger than a typical atomic radius, yet small enough to provide quantum confinement of electron and holes in all three spatial dimensions. What is meant by semiconductor quantum dots? Semiconductor quantum dots are nothing but it's a nanoscale material clusters of compounds nearly to 10 square or 10 to the power of 5 atoms. The size of quantum dots is orders of magnitude larger than a typical atomic radius. Consequently, they are also referred as artificial atoms. A unique property of the semiconductor quantum dots is that the energies and wave functions of the quantum confined states can be tailored by controlling their size, shape, and composition. The semiconductor quantum dots are typically fabricated either by chemical synthesis or exponential growth. The chemical fabrication methods have the advantage of being inexpensive, but the exponential quantum dots have several important benefits, including the possibility of direct integration in a high quality crystalline matrix, which provides high optical quality and enables fabrication of optical and electrical devices exploiting exponential heterostructure technology. The most widely explored type of exponential semiconductor quantum dots are semiconductor dots are the coherently strained exponential in as quantum dots obtained by Stranky Krustunov growth on gaseous surfaces. Moisen et al. 1994, Madhukar et al. 1994, Leonard et al. 1994. A single in-as by gas quantum dots has proven to be a beneficial model system for a broad field of experimental quantum mechanics, including the studies of light matter interaction and cavity quantum electrodynamics. Yosei et al. 2004, as well as coherent control experiments Dory et al. 2016. From application point of view, significant effort has been dedicated to the development of efficient single quantum dots based sources of non-classical light for producing Signal Entangled Chen et al. 2016 or Indistinguishable Santori et al. 2002. Photons on demand for application in quantum communication and cryptography. Such applications usually require integrations of quantum dots in optical microcavities or other small scale phonetic structures in order to obtain high brightness and efficient photon extraction. In turn, this requires precise positioning of the quantum dots with respect to the phonetic structure in order to enable interaction with the strongly localized field in the microcavity modes. To this end, site control epoxy has emerged as a favorable fabrication approach enable deterministic control of the quantum dots, nucleation sites and providing additional possibilities of turning the quantum dots properties. Quantum dots are sometimes referred as artificial atoms, emphasizing their singularity having bound distinct electronic states like natural occurring atoms or molecules. It was shown that the electronic wave functions in quantum dots resemble the ones in real atoms. By coupling two or more such quantum dots, an artificial molecule can be made exhibiting hybridization even at room temperature. Quantum dots have properties intermediate between bulk semiconductors and discrete atom molecules. They optoelectronic properties arrange as a functions of both size and shape. Large quantum dots of 5 to 6 nano diameter emit stronger wavelengths with colors such as orange or etc. Smaller quantum dots 2 to 3 nanometers emit shorter wavelengths yielding colors like blue and green. However, the specific colors vary depending on fact composition of the quantum dots. Benefits or advantages of quantum dots. What are the benefits or advantages of the quantum dots? Here are the few points that are advantages of quantum dots, and they are: number 1, they are widely used in television industry due to ultra high definition colors and increased effective viewing angles. And number 2 is thin layer of quantum dots on normal glass cloud could have lifetime of up to 14 years. Number 3, they are compatible with chip technology. Number 4 is it is easy to alter wavelength of light emitted in 400 to 4000 nanometer range to produce different colors. Number 5 is quantum dot cells can be prepared via low cost solution phase chemistry methods. They are amenable to high speed printing techniques. What are the disadvantages of quantum dots? CDSC based quantum dots are highly toxic and require stable polymer shell. Number 2, the shells can alter the optical properties and it is also hard to control size of the particles. Number 3, degradation of quantum dots inside the living organism has been studied. Number 4, overall conversion efficiency is lower. Number 5, lower temperature operation. Number 6, device production yield. Number 7, decoherence. Next one. See, by looking at these pictures, we have an idea about the light emission photocolumn sense illustrated in the figure on the right. The color of that light depends on the energy difference between conductance band and the valency band, or transition between discretized energy states of band structure, is no longer a good definition of quantum dots. There are several ways to fabricate quantum dots. Possible methods include colloidal synthesis, self-assemble, and electrical gathering. Colloidal, what is meant by colloidal synthesis? Colloidal semiconductor nanocrystals are synthesized from solutions. Much like traditional chemical processes, the main difference is the product neither participates as a bulk solid nor remains dissolved. Heating the solution at high temperature, the precocious decompose, forming monomers which then nucleate and generate nanocrystals. Temperature is a crystal factor in determining optical conditions for the nanocrystal growth. It must be high enough to allow from rearrangement and annealing of atom during the synthesis process, while being low enough to promote crystal growth. The concentration of monomers is another critical factor that has to be strictly controlled during nanocrystal growth. The growth process of nanocrystal can occur in two different regions: focusing and disfocusing. At high monomer concentrations, the crystal size is relatively smaller, resulting in growth of nearly all particles. In this regime, smaller particles grow faster than larger ones, resulting in the size distribution focusing, yielding an imparable distribution of nearly mono dispersed particles. The size focusing is optimal when the monomer's concentration is kept such that the average nanocrystal size present is always slightly larger than the critical size. Over time, monomer concentration diminish, the critical size becomes larger than the average size present, and the distribution defocuses. And next one, what are the healthy and safety methods to be taken? Some quantum dots poses risks to human life and the environment under certain conditions. Notably, the studies of quantum dots toxicity have focused on particles containing cadmium and have yet to be demonstrated in animal models after psychologically relevant dosing. In vitro studies based on cell cultures on quantum dots toxicity suggest that their toxicity may derive from multiple factors, including their psychochemical, physicochemical characteristic and their environment. Assessing their potential toxicity is complex, as these factors include properties such as quantum dots size, charge, concentration, chemical composition, capping ligands, and also on their oxidative, mechanical, and pytolic stability. Many studies have focused on the mechanism of quantum dots cytotoxicity. Using model cell structures, it has been demonstrated that after exposure to ultraviolet radiation or oxidation by air, releases free cadmium ions causing cell death. Group 2 and Group 6 quantum dots also have been reported to induce the formation of reactive oxygen species after exposure to light, which turn can damage cellular components such as proteins, lipids, and DNA. Some studies have also demonstrated that addition of ZNS shell inhibits the process of reactive oxygen species and cadmium ions quantum dots. Optical properties. In semiconductor, light absorption generally leads to an electron being excited from the valency to the conduction band, leaving behind the hole. The electrons and the hole can bind to each other to form an excitation, which this excitation recombines. The excitation energies can be emitted light. This is called fluorescence. In a simplified model, the energy of the emitted photon can be understood as the sum of the band gap energy between the highest occupied level and the lowest unoccupied energy level. The confinement energies of the hole and the excited electron and the bound energy of the excitant. Applications. What are the applications of the quantum dots? They are quantum dots are particularly promising for optical applications due to their high extension coefficients and ultra fast optical non-linearities with potential applications or developing all optical systems. They operate like a single electron transistors and show that Colombo blockade effect. Quantum dots have also been suggested as implementations of qubits for quantum information processing and as active elements for thermoelectrics. Tuning the size of quantum dots is attractive for many potential applications. For instance, larger quantum dots have a greater spectrum shift towards red compared to smaller dots and exhibit less pronounced quantum properties. Conversely, the smaller particles allow one to take advantage of more subtle quantum effects. By seeing this image, we can understand, right? Greater spectrum shift towards red compared to smaller dots. Quantum confinement in semiconductors. In a semiconductor's crystallite whose size is smaller than twice the size of its excitation bore radius, the excitations are squeezed, leading to quantum confinement. The energy levels can then be predicted using a particle in a box model in which the energies of states depend on the length of the box, comparing the quantum dots size to the Bohr radius of the electron and hole wave functions. Three rigmies can be defined as strong confinement. Rigmy is defined as a quantum dots radius being smaller than both electron and hole Bohr radius. Weak confinement is given when the quantum dots is larger than both. For semiconductors in which electron and hole radii are markedly different, as intermediate confinement rigmy exists where the quantum dots radius is larger than the Bohr's radius of one charge carrier but not the other charge carrier. And that's it. Thank you. Thank you, one and all.